We're the Council of Monte Carlo. We would like to give you our presentation on how we've approached challenge number 8. Tick. Our agenda structure was we just give a background to the project. We will talk about the problem statement we've been given and some user stories. We will look at the Monte Carlo analysis method and why we're using it. I'll give a short presentation on the data preparation tasks that we undertook. I'll cover off the results and the conclusions we have from that analysis and hand over to David to talk about our key findings and any further work. So the A14 project was really an upgrade to the existing road. The details of that, suffice to say that the project is now completed. It did complete ahead of schedule and its cost was 1.5 billion. Please. Highways England, who are managing this project, obviously they need to provide contingency funds to support the risks. They have a method for doing that, which is really to take two totals and make an average. So each risk has 3 points of estimate, best, likely, and worst. They add up all the bests, they add up all the worsts, and they take the average of those two, and that's how much money they provide as a contingency fund to support 50% of those risks. We've expanded that into 2 user stories, and our brief for this exercise is simply to provide a diagram showing the percentage confidence levels for a range of contingency fund amounts to support a decision process. What is the Monte Carlo method? Well, we've got over 300 risks to evaluate, sorry, 3,000. Each of them has 3 points of estimated cost, the best, the likely, and the worst. And there's an example of one of the risks that we have. Now, we ought to evaluate all possible combinations of outcome for all the risks, but this would be excessive. So instead, we create 5,000 random simulations of all the risks, and we evaluate the outcome from that. Now, these random simulations, the likely outcome in the middle there is favored by a factor of 90%. It's not a uniform distribution. We'll summarize these total costs for each combination. Again, look at the range of percentage confidence intervals, and we will be able to address the statements like there is a P% chance that the contingency fund of F will be sufficient, or conversely, if we have a contingency fund of F, it'll cover P% of our risk exposure. Please. This is our data preparation process. We had the original data in Excel. It was too cumbersome to really do much manipulation. We didn't get much narrative or contextual information in it. There was a lot of superfluous information. We used Python to get rid of that extra information and then loaded the trimmed down data back into Excel to process using an application called @risk. Just a reminder of the current method, which is just taking 2 averages, the best and the worst. In that case, the contingency fund of 169.4 million was necessary to set up a support for the project for one particular month. And this is to cover 50% of the risk exposure. So 169.4 million for 1 month. Next, please. After our simulation, then you can see we have the histogram chart on the left, the frequencies peaking in the middle between 140 and 200 million as our possible outcomes. We have the cumulative frequency curve in the middle, which is then producing that table on the right-hand side from which we can read that in order to cover 50% of those risks, we actually should provide 168.9 million, not 169.4. Next slide, please. So after the simulation, we can show that we can reduce this provision of 168.9 with a monthly nominal savings of $500,000 over the life of the project. And conversely, if we were to maintain 169.4 million, that would in fact support 55% of the risk coverage and not 50. Over to you, David.
Great. Well, we had 2 questions for us. The first was, what advice would you give to Highways England as a consequence of your analysis? As we have demonstrated through this project, we have shown that there are opportunities to look further into the simulation of project risk with accompanying opportunities to reduce contingency funds. And we strongly advise Highways England to look into these opportunities, although there are broader challenges to make Highways England datasets fair, that is to say, findable, accessible, interoperable, and reproducible to facilitate this across the entire Highways England project portfolio, rather than limit it to a single project context. Number 2, if you had access to actuals for risk and variance, how would you adjust your approach? Would you still use Monte Carlo methods, or would you move towards machine learning, and why? Most likely we would keep the modeling approach the same. We would use the difference between the predictions and the actuals to create a coefficient, that is to say a number between 0 and 1, that acts as a correction factor to refine existing processes. We think that machine learning will probably be overkill for the size of the data set that we have. Ideally, a machine learning data set has tens, if not hundreds of thousands, if not millions of data points, whereas we've only got 2,000 realistically. Linear regression, logistic regression are just totally inappropriate for our needs. Artificial neural networks, you need much, much bigger data sets, but decision tree models have been applied in the literature and they are worthy of investigation. But again, we're concerned about the size of the data set. Thank you.